Albert Einstein was born in Ulm in 1879. He supports the particle theory, and he founded the photon theory of light. De Broglie was born in 1892. He developed the quantum mechanical concept of wave-particle duality. Schrödinger was born in Vienna. He created the famous mental experiment of Schrödinger's cat. He supports the wave theory of electrons. Niels Bohr was born in Copenhagen. He holds up the wave motion of the electron. Werner Heisenberg was born in Würzburg. He sustains the wave nature of the electron. Max Born was born in Breslau. He is known for his researches on quantum mechanics and optics. Distinguished colleagues, we gathered here in order to discuss about the nature of the electron.
Excuse me, aren't we at the Mushroom Festival?
I'm sorry, but this is a conference about the composition of the light.
Sorry.
Look at it, guys. I'm sorry for the interruption. Distinguished colleagues, we gathered here in order to discuss about the nature of the electron. Does it behave like a wave, according to Young's theory, or like a particle, as Newton said?
Good morning, everyone. My humble thought is that, yes, practically, but in my opinion, there are electrons that...
Shut up! I am a father of physics, like my colleague Newton.
As apocalypse finally came, calculations that Newton made were right. Well, in this case, I'm going to present my theory about the nature of light. It is composed of matter particles spread by bright sources in a straight line. Thanks to these achievements, I have been able to explain the propagation of light from the sun to the earth and the reflection phenomenon.
I claim that light is composed by particles that have a wave motion. In fact, lambda is equal to h on m multiplicated v, where h is Planck constant.
On the contrary to what the bello said, I would say that light behaves like a wave. But since I can know either the speed or the position of an electron, I can't say if what the audience says is true or not.
I suppose I've been waken up to present my theories about the nature of the light. My experiments led me to the conclusion that light consists of mechanical waves propagated by bright sources' vibrations. In 1678 I explained waves diffraction, assuming that every point to which a luminous disturbance reaches becomes a source of a spherical wave. The sum of these secondary waves determines the form of the wave at any subsequent time.
Before exposing my theory, I would like to hear what Schrödinger has to say. Well, Schrödinger is in no position to answer, so I'll talk first. A long time ago, while I was looking for a solution,
if I had a device that shot single electrons through two slits at very close distance, a screen behind two slits that could detect every single electron, and I did not know in which slit to the electron pass, we could notice on the screen some fringes composed of electrons, similar to those of light diffraction. On the contrary, if we placed an observer to detect in which slit the electrons pass, we could see only two fringes instead of diffraction.
Let me go! It's my turn! I formulated the wave equation based on an approach which allows to represent the particle through the wave function. Then the light is composed of particles, and as my predecessor Thomson has shown, electrons are particles.
I'm J.J. Thomson, and in order to witness that light behaves like a particle, I did an experiment in 1897 with the Crookes tube. Now, for those who don't know it, the Crookes tube is a cold cathode tube containing gas. When high voltage is applied to the tube, the electric field accelerates the charged ions in a gas and makes them collide against the gas molecules. This process creates more positive ions, which are attracted to the cathode. The formation of the positive ions is due to the electrons in the molecules, which form the light, confirming my theory on the light behavior.
Light is a wave because it propagates in the vacuum.
Greetings everyone, I'm Thomas Young, or I should say I was. My experiment about the interference is called double slits interferometer. This is one of my most important achievements. This experiment played a major role in the general acceptance of the wave theory of light. I put two light sources in front of two slits narrow enough to create an interference phenomenon, characteristic of the wave. I placed a black body phased with the slits, which absorbed the light, creating the interference pattern.
If it was a particle, it would refer to a mechanical wave which cannot propagate in the vacuum. So the electromagnetic wave propagates in the vacuum, and thanks to the intensity variation of the electric charge, which interacts with the near ones. So, based on what I had just said, I'm right, and you are wrong. I am right, you are wrong. We had to sort it out like real men. Rock sheets of paper. Rock sheets of paper. Yes, I'm a winner.
In 1927, my colleague Lester Germer and I conducted an experiment which demonstrates the Bernoulli hypothesis about the wave properties of electrons.
In fact, we demonstrate that electrons, which are particles of matter, can have wave properties. We fired an electron beam toward the nickel crystal.
The incident between the beam and the crystal formed the phenomenon of the diffraction, that is typical of waves. In conclusion, electrons act like waves.
In May 1974, Pier Giorgio Merli, Gianfranco Missiroli, and Giulio Pozzi sent an article to the American Journal of Physics entitled "On the Statistical Aspect of Electron Interference Phenomenon," which was published 2 years later. 30 years on the September 2002 number of Physics World contained the results of a survey in which readers had been asked to name the most beautiful physics experiment. The reader's leading choice was Young's double-slit experiment, applied to the interface of electrons. In the May 2003 number of the same journal, the above-mentioned Italian scientists were acknowledged as being the first to conduct the aforesaid experiment, reference being made to their article published in 1976.
Good morning, I'm Missiroli, and these are my colleagues, Merli and Pozzi. Today we want to show you the most beautiful experiment in physics.
This experiment will allow us to prove if the electron acts as a wave or as a particle.
The experiment allows us to obtain an interference pattern through a standard electron microscope, fitted with a special interferometer called electron biprism.
The electron biprism basically consists of a very thin wire and the right angles to the beam, positioned symmetrical between two plates and the ground potential.
We applied a positive or a negative potential to wire, so that an electron beam is split into the flat component. The use of electron biprism is the first important technical and conceptual feature of this experiment.
Well, the second fundamental aspect, of course, is that change its beam to observe the continuous arrival electron, one at a time, on a television screen.
The Duncan double-slit interference experiment has also been of vital importance in relation to the employment of probability in quantum mechanics. According to some authors, the experience represents the most striking proof that the axiom of the countable additivity probability is not valid in quantum mechanics.
The notion of non-locality is intrinsic in the Gedanken double-slit experiment, when it is said that the particle knows whether the slit through which it didn't pass is open or closed, and it knows of decision to measure or otherwise its trajectory, even though the said decision is taken after it has passed through the slit.
Furthermore, the experiment can be seen as a pair of double-slit experiment in which the result of the decision to carry out a measurement using one microscope should immediately modify what is observed in the other microscope. The presence of otherwise of interference fringes.
The way we have chosen to realize the interference of the electron is different from that of Twinger, where a special equipment was built for the experiment. We have decided to change a standard electron microscope, creating a version of the biggest moleskin Dunker. That can be mounted inside of the microscope using the space where the compounds are usually put in order to observe.
Using a new detector invented by Hermann, we can make an experiment in which we can highlight, in the same time, it traces of the individual electron and formate the fringes formed by the accumulation of these traces.
The image of interference highlights the individual breakpoint of the screen detector accumulated in the medium time, forming the fringe typical of wave, and not the one in which electrons form two separated strips.
When each electron is displayed in a precise position, it is identified by the green spot it produces. The electrons behave similar to waves.
In conclusion, to the famous question of the whether electrons are waves or particles, we can answer that they are actually both.